Hi, everybody, and thank you for attending this webinar. My name is Edin Zulich, and I'm a NoSQL Solutions Architect focusing on DynamoDB. Today, I'm going to talk about migrating from Cassandra to DynamoDB. This talk is based on our customers' experiences migrating from Cassandra to DynamoDB, and it's about their insights from these migrations, why they migrate, benefits they get, and how they go about it. So we only have about an hour, so we're not going to get into too much detail here, but I'm hoping that we can cover all the important concepts. The agenda for today, we're going to start with a quick Cassandra DynamoDB overview. After that, I will talk about why customers migrate from Cassandra, why they choose DynamoDB, and benefits they get from migrating to DynamoDB. Then I'll focus on the steps involved in the migration process and how to do each one of them. After that, I have a few frequently asked questions that come up when we engage with customers around these migrations, and then we'll wrap it up. So this is a high-level comparison. Both Cassandra and DynamoDB were inspired by the original Dynamo paper that came out just over 10 years ago. They're both NoSQL databases, and they have a lot of similarities. For example, they're both used for similar use cases and requirements. Scalable NoSQL store. They're both prized for their good performance. They're both good at storing time series data, and they both have features that allow you to replicate data even at a global scale. Both are also API driven, but they have different APIs, as there's no standard API for NoSQL. So that means that migrating involves writing a new database access layer, and in this case, that will be for DynamoDB. Now, they have different capacity and cost model. Cassandra is instance-based, while DynamoDB is fully managed, and it's therefore request-based. Fully managed means that you don't get to see any instances or clusters. So while with Cassandra, you have to manage your cluster and instances. With DynamoDB, you just consume a fully managed service, and somebody else takes care of managing the clusters and the infrastructure. So on the one hand, instances can absorb bursts as essentially they over-provision, right? And request-based model, on the other hand, scales more seamlessly and incrementally, and it also allows you to scale down better. Why customers migrate from Cassandra? Or actually, a better question might be, or any other non-relational database for that matter. As they grow and scale their databases, database maintenance becomes harder. This is not a problem with just Cassandra. Some customers have migrated from Cassandra to another database only to face the same growing pains and challenges. Non-relational databases are distributed technologies designed to scale horizontally by adding nodes. Also, distributed technologies are complex. So the problem is as the scale grows and you add more nodes, your database operations become more challenging. At Amazon, we learned this the hard way. In fact, managing Dynamo. And at some point, we also realized that database operations were consuming too much time and effort, and they were getting in the way of your core business. And so here we also see a couple of different customers and their testimonies about growing pains with managing their own clusters. So to sum it up, and this is really true of all distributed data technologies, operational challenges grow with scale. And that leads to increased complexity, increased resource use, and cost. And this is really true for all distributed clustered databases. So like I said, with Dynamo, we had pretty much the same experience, and DynamoDB was created to address that problem by providing a fully managed service. So why DynamoDB? Well, here's one example. As a fully managed service, DynamoDB serves a number of applications at Amazon. And one really big test for DynamoDB is Amazon's Prime Day. And this last Prime Day, the requests to DynamoDB totaled over 3.3 trillion. and peaked at almost 13 million per second. And it was really the extreme scale and consistent performance as well as high availability of DynamoDB that allowed such an event to really go without breaking a sweat at such a massive scale. And it's not just Amazon, right? DynamoDB is now in use by over 100,000 AWS customers in a wide variety of use cases. They all have one thing in common. They are mission-critical applications where availability, scalability, and performance really matter. And for all those things, they depend on DynamoDB. In other words, DynamoDB is a battle-proven technology in mission-critical applications that require massive scale and reliability. Now, the thing about it, though, is that DynamoDB is not just a database. It's also a service that runs your database, so you don't have to, so that you can focus on your business instead. So Amazon DynamoDB is a fully managed NoSQL database service that runs in AWS Cloud. The complexity of running a massively scalable distributed NoSQL database is managed by the service itself. So the service has built the know-how and experience in managing massive scale database service that DynamoDB is. Now that allows you to focus on building applications for your business rather than managing database and the database infrastructure. As NoSQL databases are designed for scale, but their architectures are sophisticated, there can be significant operational overhead in running a large NoSQL cluster. And like I said earlier, we learned this hard way with Dynamo, the original NoSQL data store that was developed with Amazon. And because of that, we developed DynamoDB to be a fully managed database and therefore much easier to use. In addition to being easy to use, DynamoDB is also cost-effective. With DynamoDB, you pay for the storage you're consuming and the read and write throughput you have provisioned. It's designed to scale elastically while maintaining high performance. When the storage and throughput requirements of an application are low, only a small amount of capacity needs to be provisioned in the DynamoDB service. As the number of users of an application grows and the required read and write throughput increase, additional capacity can be provisioned on the fly. And that can be done using either auto-scaling or explicitly. So this enables an application to seamlessly grow to support millions of users, making thousands of concurrent requests to the database every second. And finally, DynamoDB is secure with support for end-to-end encryption, fine-grained access control, as well as VPC endpoints, which allow you to access the service from the privacy of your VPC. Over the last year, there's been a steady cadence of new features released in DynamoDB. Time to live, or TTL for short, allows you to scale down the storage and save on cost by letting DynamoDB automatically remove expired data with no extra cost. VPC endpoints is a feature that allows you to access DynamoDB from the privacy of your VPC. DynamoDB Accelerator, or DAX for short, reduces the read latency below 1 millisecond and allows you to scale to millions of reads in a cost-efficient way. It's a front-end cache for DynamoDB. Auto-scaling ensures that you have the capacity when you need it, while saving on cost by reducing it when it's not needed. Global Tables is another one of the key features that allows you to replicate your data between different regions seamlessly using built-in support for replication that Global Tables provides. Backup and recovery. In December, the service released on-demand backup, and in March this year released point-in-time recovery, or what we also know as continuous backup feature. And also this year, encryption at rest has been added as well. Now finally, another feature that doesn't get much press, so to speak, is adaptive capacity. What it does, it allows DynamoDB to dynamically scale throughput per partitions that it manages for your tables based on real-time traffic. And this really avoids and solves the problem that we used to have to deal with, which we know as throughput dilution. With adaptive capacity, now DynamoDB manages the traffic automatically and dynamically for you, and you don't get the issues that you used to get with throughput dilution. Just a quick word on DynamoDB Global Tables as one of the key features that really makes DynamoDB an attractive option for workloads that depend on Cassandra for multi-data center replication. This feature was built for high-performance, globally distributed applications and provides low latency reads and writes to locally available tables, right? The two use cases that Global Tables is designed for is disaster recovery or business continuity, because it allows you to replicate your data seamlessly between multiple regions. Also, it allows your applications to provide data where the users are, so geo availability of your data and low latency. Global tables are really easy to set up, and there's no requirement to rewrite your applications to use global tables. So across the board, we observe the following benefits that our customers see upon migrating to DynamoDB. The most important one is the stability and performance at any scale. That's really the number one reason why they needed to migrate. They get single-digit millisecond latency for reads and writes at any scale. Then elastic provisioning with DynamoDB with auto-scaling, as well as also the ability to use explicit APIs to change your provision capacity, is another very useful feature and benefit that our customers like, not to mention zero maintenance and operations overhead, right? With DynamoDB, you don't even get to see database clusters or nodes. So therefore, you don't need to worry about the resources, CPU, memory, and so on, not to mention patching the OS, hardware maintenance, and so on. It's a zero maintenance and operations overhead service. And finally, in addition to all these things, our customers see cost savings over Cassandra, typically between 30 to 70%. So let's talk about the migration process now. Successful migrations are carried out in a well-planned manner and in multiple steps. Typically, it takes several iterations to get everything dialed in. And what these steps look like is going to be application specific. These migrations are more of an application migration than a data migration. One example is actually the largest migration to DynamoDB to date by Samsung for their Samsung Cloud service. This service provides backup and restore and key value store for mobile application by Samsung. It has about 300 million users. The entire migration process took roughly about 12 to 13 months. And now they have almost 1 petabyte of data in DynamoDB and are basically running at about 130 million daily API requests. They've also seen consistent performance over time, as well as 70% cost savings, TCO. First step in any migration is to define requirements, scope, and goals of the migration. And like I said, this is going to be application specific. Some of the concerns, for example, include whether any downtime is allowed for cutover, how long. Typically, though, today we see that most customers want to do live migrations with no downtime. This can also be an opportunity for spring cleaning. Some of the data might not need to be migrated, and there might be quite a bit of such data. And that's something that can also be planned for. Good steps to do as part of planning phase is documenting per table requirements as well as challenges, and then defining and documenting backup and restore strategies. Next, data analysis phase provides answers to questions we will be asking when we do data modeling and capacity planning. They will also help inform our choice of migration approach. So for application access patterns, we need to know what kind of writes and updates the application does, if it uses any transactions, and what kind of queries it does, as we will be mapping these to DynamoDB. Source data analysis is another very important aspect of data analysis. We want to know some of the key data attributes. What's the cardinality of items to be migrated? In other words, how many rows are to be migrated? What are the item sizes? And then what's the multiplicity of values that will be used as partition or sort keys? Data lifecycle is another important point because it can inform our decision how to do the migration itself. Once we've done the data analysis, we can go on to do data modeling and capacity planning. And this is where we use the results of data analysis, because now we know what the access patterns are, and we use those access patterns to define instantiated views based on those. We need to define a partitioning scheme, which is also what allows your data volume to scale, as well as your workload, in fact, to scale as well. This will likely be the same as in Cassandra, because they're both similar in that sense, being NoSQL data stores that use partition key to shard data and scale out. Then we need to think about defining data structure. What are records, what we call items in DynamoDB, going to look like? Are we going to use document style data structure, or maybe an item hierarchy? For example, in Cassandra, you can use wide rows. In DynamoDB, we usually map those into what we call item hierarchies. So we pivot those tables, and instead of using wide rows, we would use multiple rows. So in other words, data structure may not be the same as in Cassandra. And also with DynamoDB, we have streams and triggers, which are equivalent of stored procedures. And so we need to think about those use cases as well. With DynamoDB, data modeling and capacity planning are closely related. Data model will define not only the structure of data, but also what reads and writes will look like. So let's do a quick refresher on some of the DynamoDB fundamentals. In DynamoDB, we store data in tables, and that's really the top level concept in DynamoDB. The table consists of items, which are also known as rows in other databases. Each row can have multiple attributes, and it can vary from one item to the next. Partition key, much like in Cassandra, is mandatory, and it defines the key value access pattern, and it also defines how data is going to be distributed in DynamoDB across partitions. Sort key is optional, and it really is equivalent to the Cassandra clustering key. It's used to model one-to-many relationships, and it also enables rich query capabilities. We use sort key, for example, to store data that's sorted based on time, for example. A quick overview of data types. Nothing unusual here, but you will notice that there's no timestamp or date-time data type. For date or time data, you need to use number or string. And if you're using time to live in DynamoDB, that has to be a number that's in Unix or epoch format. Otherwise, you can also use string. And if you're using ISO 8601, your data will be ordered and therefore sorted when it's stored in DynamoDB. Let's talk a little bit about provision throughput capacity. It's provisioned per table or global secondary index. And capacity is provisioned per second, rounded up to the next whole number. There are two types of throughput capacity: read capacity, which is measured in read capacity units, And each RCU returns 4 kilobytes of data for strongly consistent reads or 8 kilobytes of data for eventually consistent reads. And you can select whether your read operation is eventually or strongly consistent using the appropriate option on the read request, read consistency option. Write capacity unit writes 1 kilobyte of data, and each item write will consume at least 1 write capacity unit. Global secondary index will get its own dedicated capacity, and when you query GSI, you consume only the capacity for the GSI. Now, a quick overview of how to model hierarchical data in DynamoDB. One way of modeling hierarchies is to use item hierarchies. And in this example, we see that same partition key, which is in this case product ID, actually is used in multiple rows in the table for multiple items, but they have to have a different sort key. And in this case, we use a composite sort key to define a hierarchy. And that allows us to query data and return 1 or more items at a time. Now, this is really important if you have large hierarchies and you need to update data in small chunks, so to speak, in smaller items. If you were to store the entire item or the entire logical record in a single item, updating that would be consuming the write capacity that's equivalent to the size of the entire item. However, if that logical document or record is split into multiple items, then updating a single item will therefore consume a lot less write capacity. So as we see here, we're talking about consuming capacity as we're doing the modeling, right? And that's really important to understand with DynamoDB. Another approach is to store hierarchies as documents using JSON format. DynamoDB supports document SDKs. And probably one key thing to keep in mind here is the limitation on the item size, which is 400 kilobytes in DynamoDB. Now, with respect to this limitation, there are multiple ways of dealing with that. For data that doesn't need to be queried, those attributes could potentially be compressed. For example, in this case, if we have large documents that we store in a single attribute as a JSON document, we could compress the entire thing. And we can extract only those attributes and make them top-level attributes in DynamoDB that we need to query on. So in this case, that could be title or artist or genre. And otherwise, if the documents can get really large, we can compress them, or alternatively, store them somewhere else, maybe in S3. And that's what's typically done in case of blob data types. Capacity planning for DynamoDB is about reads, writes, so I/O throughput, and storage for your tables and indexes. There are no nodes or clusters, so there's no capacity calculation for how many nodes you need in a cluster and what instance types you need to use for each node and so on. However, a good design should provide for a cost-effective solution, and that means that cost can influence design. And that's why it's important to understand the cost model in DynamoDB as well. So in addition to these considerations, one other thing that is really important to think about here is capacity during migration versus after migration. For one, we need to be able to answer the question, is there going to be an initial data import phase? And if so, we should make sure to provision sufficient write capacity for import during migration. Then when the import is done, migration is over, we can change that to better fit our normal operation needs. Application development and operations. One thing that we'll have to do is create a data access layer for DynamoDB. As part of that, we should be thinking about dynamic application configuration, especially in the context of live migrations, because we should be able to write and read to and from both source and target database. And that would allow us to support gradual switchover and also to switch back if we need to. And then, of course, need to make sure to test rollback, backup, and restore procedures. Let's take a look at one customer example. This is a customer gumgum, and in fact, their migration is well documented, described in their own blog post, and which is referenced right here. In their case, they had the lifetime of data that was about 30 days. And that meant that after 30 days, data becomes unusable or basically not relevant anymore. And so when they were approaching the problem of how to do the migration, they took that into consideration and said, well, if we write both to Cassandra as well as DynamoDB over a period of 30 days, eventually we will have all our data in DynamoDB as well as Cassandra, and from that point on, we can do the switch over. And that's exactly how they did their migration. So after about 40 days of writes, they stopped reads from Cassandra and then started reading just from DynamoDB. And so they really did not have the initial data loading ETL phase where they would have to export data from Cassandra and then import to DynamoDB. They simply decided to take advantage of the natural data lifecycle in their application and do the migration that way. And that's a fairly common approach. In fact, we see that approach in other customer use cases as well. A quick note about DynamoDB APIs. As you can see, there aren't that many APIs in DynamoDB. Some are admin, some are typical CRUD operations, as well as Streams API. However, the APIs are still actually rich with options that allow you to do conditional writes and updates. So that would be the equivalent of lightweight transactions in Cassandra. Related to those are conditional check failed exceptions that you need to make sure to handle. Consistent read parameter is the parameter that's used with get item, scan, and query operations to specify whether that read should be consistent or eventually consistent. Filtering APIs, we have filter expression so that you can actually tell DynamoDB to filter data from the result set on the server side. You can also specify the sort order when you have sort key. Limit has the same purpose as in Cassandra. You can limit the size of the result set returned. There is a support for pagination as well, which is based on the parameters called last evaluated key and exclusive start key. And then a couple of exceptions that are probably at the top of the list of the exceptions to know about: throttling exception and provision throughput exceeded exception. These exceptions are thrown back to your application when you exceed provision throughput or when DynamoDB is throttling your requests for other reasons. Return consume capacity is an option that you can specify on your request so that the response from DynamoDB will include the capacity that was consumed by the request. Support for rich expressions is also there. You can specify projections Also, filter expression, which I just mentioned, conditional expression, which allows you to do writes or updates or deletes based on a condition. This is really a key construct for maintaining consistency of updates to your data in DynamoDB. This is how we implement optimistic concurrency control in DynamoDB using conditional writes. And then update expression is another one. For error handling, it's important to know that there are roughly, at a high level, two types of errors, 400s and 500s. A 400 error means there's a problem with request. A 500 error means that the problem is on the service side. And you handle each one differently. For problems that are 500 error types, it's okay to retry immediately or after a short delay. 400 errors should be evaluated. The most common type is provision throughput exceeded exception. And in this case, you can use exponential backup to retry. For operations, some of the key points is one is security and access control, which for DynamoDB is implemented using AWS Identity and Access Management. Deployment is typically done via AWS CloudFormation, and then monitoring is done using CloudWatch, CloudTrail, and as well as AWS Config. A lot of our customers use enhanced monitoring offerings by some of the third parties, AWS partners. You can also create your own application metrics and monitor those as well. Data migration approach will depend on application. Right? So, for example, it could be based on data lifecycle, which we saw in case of gumgum. Data is stored for a set amount of time, and we can take advantage of that as we migrate. In phase one, we write to both, but we read just from Cassandra. And then after that, when all the data is in both data stores, we start reading from DynamoDB. The approach could be incremental. For example, you could decide to migrate users sort of one at a time, right? And in other words, the idea is to migrate each user's data as quickly as possible. Of course, you're migrating multiple users, but the idea is to never migrate or to never split data that you're migrating basically for a single user, so to speak. So a single user data set is accessed from either Cassandra or for DynamoDB. This is an approach that we'll also take a quick look at that Samsung used to migrate really large data set from Cassandra to DynamoDB. In some cases, it helps to do a batch export and import and then basically add live updates on top of those. So how data can be exported from Cassandra is something that different customers do differently. We see people write their own applications, for example. But when it comes to importing into DynamoDB, for larger data volumes, the best option at this point is to use EMR to be able to parallelize the data import and finish the whole import faster that way. If you're using EMR to import data into DynamoDB, you want to make sure to provision enough write capacity. Also keep the read capacity down during import. And that, in addition to that, you'll have to tune the EMR cluster for instance type and size to match the workload along with the DynamoDB write ratio as well. This is enabled by connector between DynamoDB and EMR. So example, Samsung did their migration for for their cloud service online, they decided that there was just too much data to do a full migration. And so they did this as a per user migration, right? So during the migration, which took about 4 months, the actual just data migration, some users were still in Cassandra while others were in DynamoDB. So because of that, they had what they call a storage path DB so that they could tell where to find a particular user. And then to minimize impact for each user, they migrated those users as soon as possible. The benefits that they got from migrating to DynamoDB, so they were able to successfully launch their Samsung Cloud service that supports massive scale workload, right, for their Galaxy line of phones. Just the infrastructure cost, basically, just in the infrastructure cost, they saw savings of 40%. And there's no capacity planning and much of it that they need to do for this massive, basically scale, petabyte scale storage with on-demand capacity. They're also seeing consistent performance at tens of millions of operations and zero administration for hundreds of tables. They haven't seen any failures during 2 years of operation, no data corruption or loss for billions of items. Another customer, gumgum, their main benefits were stability and performance to scale, 2 to 3 millisecond read and about 4 to 6 millisecond write latency, DynamoDB elastic provisioning via auto-scaling, and again, zero maintenance. And finally, their total cost savings over Cassandra were in the range of 65 to 70%. So for them, no additional infrastructure to run and no more maintenance activities from their engineering was a huge win. Right? So here I have an FAQ. These are really typical questions that come up in conversations, right? For example, people say, oh, with Cassandra, we can easily store time series data, but DynamoDB is a key value store, so it's not efficient. And that's really not true. As we could see, with DynamoDB, we can use stored keys, which are the equivalent of Cassandra's clustering keys in Cassandra, to organize data that will be very easily accessed and efficiently accessed based on timestamp. Another question is, does DynamoDB have tombstones? Or does DynamoDB do compactions? What about latency? Is there JVM garbage collection that can affect latency in DynamoDB? So the fact that DynamoDB does not use JVM is actually irrelevant. And it's an implementation detail that really does not matter. Why? Because DynamoDB is a service. It manages the infrastructure and whatever it has that stores your data. The key point is that the service takes care of all this for you so that you don't have to. And the service is designed to operate and provide performance to scale so that you don't have to worry about infrastructure management anymore. Then typically there are some questions about consistency and how DynamoDB manages consistency. With DynamoDB, it provides the option to read data in a consistent or eventually consistent manner via the consistent read option. And that's it. Dynamo replicates data behind the scenes to 3 physical locations. And that's not even configurable. But that's what allows you to be assured that your data will be always there, durable, and highly available. Another question that we get quite a bit is about wide rows, right, in Cassandra. And what about the limit size with DynamoDB? So I mentioned that earlier. With DynamoDB, the item is limited to 400 kilobytes. And wide rows from Cassandra can be modeled as item hierarchies. This is kind of basically how we map those to DynamoDB, or as JSON documents, right? And then, as we saw in that example earlier, that will depend on access patterns. And for data type, use numbers or strings. So to sum it all up, by migrating to DynamoDB, you will be trading one set of idiosyncrasies for another. From thinking about instances, you'll go to thinking about read and write capacity. And again, I should emphasize how important it is to understand the cost model in DynamoDB because of that. Also, from column families in Cassandra to DynamoDB tables and item hierarchies. However, as we see with all of our customers that migrate to DynamoDB, the benefits that you get are well worth it. No database maintenance, no clusters to manage. Scaling is effortless. You get stability and consistent performance at any scale. DynamoDB is also available in all AWS regions around the world. And that makes it really easy to stand up your applications anywhere where your users are. Agility, you don't need to set up a cluster to use DynamoDB. You can just log in and create a table either in console or using the APIs. And then finally, in addition to all this, you're likely to get pretty good cost savings as well. So keys to success really in migrating, in any type of migration, in fact, is one, understanding the source data and access patterns. You have to understand the capacity and cost and how scaling affects it. This is very important with DynamoDB. Testing, right? This is going to be an iterative process. And learn from some of the documented cases. I've added the references to those here and also a link to DynamoDB best practices. Thank you very much.